So it's a great pleasure to welcome Margaret Murnane back to Ottawa. Margaret's work is in ultrafast optics and X-ray science, but that doesn't really capture the essence of her work. She's worked in many subfields of physics: plasma physics, magnetic materials, CDI, chemical physics, many, many things. So Margaret's a fellow of JILA. She's a distinguished professor at University of Colorado. She's a member of the Department of Physics and Electrical Engineering there. Eugene pointed out that probably not very often do you have more Irish people speaking at a seminar like this, the two of them, than you would have any other nationality, but I think that might be the case here. So she received her B.S. and M.S. from degrees from the University College in Cork, Ireland, and her Ph.D. she came to the U.S., where she went to Berkeley in 1989. She joined the Faculty of Physics at Washington State in 1990. In 1996, she moved to Michigan, and in 1999, she moved to Colorado, where she's stuck ever since. She has many awards. I had too many for me to name, but I'm going to just pick out what, to me, are the most impressive. I don't know. I think you will think they're impressive, too. So in 2004, she was elected a member of the National Academy of Science in the U.S. This is a huge thing in the U.S. In 2006, she was elected a fellow of the American Academy of Arts and Science. In 2009, she won the Ahmed Zewail Award in the American Chemical Society, which she shared with Henry Kapteyn. So that's the chemistry prize. In 2010, she won the Woods Prize of the Optical Society of America. She shared it also with Henry. And so that's the Optical Society of America Prize. In 2010, she also won the Arthur Schawlow Prize for Laser Science. So that's the American Physical Society. So there are the three main societies in which optics plays a, I'm sorry, SPI. One of the three of the four main societies in which optics plays a role. I'm sorry. I didn't mean. Yes, I know you have to compete. Yeah, yes. And this year, I think it's this year. I know it's this year, as a matter of fact. This year, she won the highest award of the Optical Society of America, the Ives Medal. So it's really a great pleasure to have you back, Margaret.
Thank you so much, Paul and Bob. I'm really delighted to be here in Ottawa to celebrate photonics, and in particular X-ray photonics. And of course, I feel a little bit like, bringing coals to Newcastle. But well, I'll talk about some work that's complementary to the beautiful work that Paul is leading here. And so what I'd like to try and convince you is that this high harmonic generation, we know it's very beautiful quantum physics, but I'm going to try and convince you that it really now has stepped up and moved past the initial proof of concept demonstrations, and that it really now is a quantum technology that has real-world applications in materials and nanoscience and imaging, and that lets you see things that you simply can't see with visible light, synchrotrons, or X-ray free electron lasers. And I want to compliment all the previous speakers, and so my talk will build upon yours. Eugene told us the wonderful stories about the laser science, the early days of laser science. And for those of you who don't do short wavelength science, you may not realize how far we've come in terms of wavelength. We're celebrating everything we're doing in the nonlinear optics, in applications, in industrial impacts, machining, LASIK, all of these wonderful things. But there's one area where we haven't moved very far in terms of widespread applications of lasers, and that's in terms of the wavelength. Eugene mentioned the critical importance of lasers in manufacturing our chips, and in fact, the shortest wavelength laser that is in widespread use is the excimer laser at 193 nanometers that is used to print our chips. And so what that means is that in terms of lowering the wavelength, we've moved by a whopping factor of 4 in 57 years. This quantum technology that Paul is pursuing and others are pursuing here in Ottawa is the only practical route for widespread application of coherent short wavelength beams. Of course, Eugene talked about the incoherent plasma sources that would be used to print the next generation chips using EUV lithography. Here I'm talking about coherent beams. Of course, there are X-ray sources that are in widespread use, for EUV lithography, whenever we go to our doctor or dentist's office. But when you sort of look at what the radiologist is often staring at, it actually doesn't look a whole lot better than the first X-ray that Röntgen took of his wife's hand. And basically it's because modern X-ray tubes are a higher power version of the first X-ray tube that Röntgen demonstrated. So basically you're taking a picture with an X-ray light bulb. And one way to get to the wavelength limit in terms of X-ray imaging, one way is to make an X-ray laser. So why not do that? Well, I think this audience knows very well why that's challenging, and it's because we've known from the time of Einstein what the ratio is between spontaneous and stimulated emission, and so we can do a back-of-the-envelope calculation to see what the scaling is for powering an X-ray laser based on traditional population inversion. And you can prove to yourself that that scaling just goes something like the wavelength to the inverse 5th power. And what that means is, we can hold a laser pointer or even a more bright laser pointer that I wouldn't, how many milliwatts is that pointer? But anyway, I can hold a laser pointer in my hand because I only need a milliwatt to power a laser in the visible and near infrared. But by the time you try to make a laser that lasers at 1 nanometer wavelength, that would take a terawatt of power. So that's on order of the electrical generating capacity of the United States. So we're not going to make a continuous wave X-ray laser. And if you go to an angstrom, then you're talking about a petawatt of power. And for that reason, some of the first X-ray lasers were observed, at least we believe, during nuclear weapons testing, because that puts a huge amount of energy into systems. And back in the 1980s, for those of you who remember the 80s, there even was a proposal to shoot down missiles by detonating a nuclear weapon in space. And it's for that same reason that, and we heard from Keith and Eugene, that the first coherent X-ray beams were made not based on population inversion, but rather based on electron accelerator technology, wriggling electrons in the right way so that they make a coherent beam of light. And that first light came just about 50 years after the demonstration of the visible laser at the X-ray free electron laser at Stanford, lased about 1.5 nanometers. And so there was celebration because of the free electron lasers, and then we had the Laser Fest 50-year anniversary of the laser. And I always loved Steve Chu's comment. Steve Chu was Secretary of Energy in 2010. And what Steve is famous for is good wit, and what he said is, and they're marvelous machines, you can do marvelous science with them, but they certainly are not free, and I should know it, because of course he had to put on order of $1 billion budget per exfil, and more with the upgrades. Now, of course, there's absolutely gorgeous science, and Keith presented some of that. It's really pouring out of these machines, but it is well worth our while also seeing, well, what part of this science and technology can we do in a tabletop scale apparatus, because that's what's going to have impact on nanomanufacturing, material science, and other potential, and I apologize on this. And what I'll try and convince you today is that we actually have very surprising control over light in the X-ray region of the spectrum, and we could have an argument over beer that we actually have better control over light in the X-ray region of the spectrum than we have in the visible. And that's something that many of us, Paul and myself, who remember trying to make X-ray beams prior to harmonic generation, we would never have expected that. Essentially, what we're doing is using a very short femtosecond laser pulse to manipulate the irradiating electron wave function. And what that allows us to do is make a coherent continuum that spans 12 octaves. That is the most spatially and temporally coherent light source at short wavelengths. We can now manipulate the polarization and essentially control X-ray beams using visible laser beams. And for those of you who maybe are not familiar with X-ray science, this is very good we're able to do this, because X-ray optics are very challenging. We do not have wave plates, polarizers, good optics, spectrometers. Most of these optics, if you put them in the beam, you're talking about at least a factor of 100 loss for the most part. So the fact that we can actually tailor the spectrum, for example, this continuous wave 12 octave spectrum was done by driving high harmonic generation with a mid-infrared laser, but this ultra narrow band peak was generated by driving high harmonics with an ultraviolet laser. So just by controlling the color of the driving laser, we can sculpt the spectrum, make linearly or circularly polarized or arbitrary elliptically polarized beams, and also generate pulses that are actually ridiculously short, and this just comes about from the physics, actually shorter than any motion in our natural world, and this comes beautifully out of the physics. Okay, so what's it? Oh, I have no idea what's going on here, but anyway. So as we heard earlier from David's talk, high harmonic generation, it's a universal response of all atoms and molecules in a strong laser field. If you put an atom or molecule in at the focus of an intense femtosecond laser, trying to get the movie to play. As the laser field increases, the atom undergoes tunnel ionization, the electron moves away from the ion, and when the light field reverses, the electron can re-encounter the parent ion and give off its excess Rigel energy as a coherent X-ray. And so what you see here, this movie shows what the two-dimensional, you can think about this as a two-dimensional movie of an electron in the ground state of hydrogen. As the electric field of the laser increases, you get tunnel ionization, but only part of the electron wave packet undergoes ionization, moves away from the parent ion, and when it recombines, because the quantum phase is different than the part of the electron wave function that didn't ionize, you get this beautiful spatially modulated nanoscale antenna. And so if I let this movie go one more time, you can see that, so the fundamental frequency, you can see, this is the fundamental laser frequency, but the presence of these spatial modulations make it look as if you're accelerating that electron at much higher frequencies. And that is the quantum origin of high harmonic generation. We sort of exaggerated the movie a little bit, but if you think back to your quantum mechanics, you can think, that tunneling is exponential in the field. So the precision at which the wave function of the electron and the generated X-rays are in lockstep with the driving laser field is actually not communicated as so well in this movie, but it is superb. I mean, we have no other X-ray light source like it in terms of the synchronization between the generated X-rays and the driving field. And everything I've told you was worked out by Paul and others back in the late 80s, early 90s. So we know, and the emission from each atom follows a dipole radiation distribution, because an electron is undergoing a transition from a high energy continuum state back to the ground state. It's a dipole transition, so the radiation is not directed. But just like in nonlinear optics, if you want a directed beam, you have to figure out how you can add the light from many atoms in the medium. And of course, for this audience, who knows photonics, you might think, you know, how hard could that be? But it took a long time, and my pet theory, let's see if Paul agrees, is that there were only a few people doing atomic physics and laser science, and for the most part we went to different conferences. And so it took our communities a long time to combine the quantum physics and nonlinear optics, because we were, the language was quite different. But fortunately we did it eventually. And our collaborator, Carlos Hernandez Garcia, made a little cartoon for us just to try to communicate, you know, why is this hard, and why is it surprising we can actually make a laser light beam by phase matching, this audience knows, or for those of you not in nonlinear optics, if you want to synchronize the emission from many atoms. So you can imagine the laser is a quantum conductor, and you're trying to make the same number of atoms as there are people on Earth sing and tune at the same time. And the challenge is the difference in wavelengths. So if we use a 4 micron driving laser to make a 1 nanometer X-ray beam, then you've got, you know, 4,000 times different wavelengths or frequencies. And you know you won't be able to add waves in phase unless you get them lined up to a fraction of the wavelength and a fraction of the cycle. And so what we're trying to do then is we have to align the X-ray fields to a sub-angstrom spatial resolution. If it's a 10 angstrom wavelength, you know you have to do at least better than 1/10. And at 1 nanometer, the cycle time is an order of 3 attoseconds. So you won't get a beam out if you're not lining up your fields to sub-angstrom spatial resolution and sub-attosecond temporal resolution. And we have no hope of doing that with electronics. I mean, we're many, many, many orders of magnitude off. And we are so fortunate that nature does this passively. Due to strong field ionization, which is exponential in the field, so the timing of when the X-rays emerge are exactly deterministic to this fraction of an attosecond with respect to the driving laser field. And that's why it all works. So it's actually just a remarkable, you know, it's not remarkable once you understand it, but certainly going in, none of us would have expected to have it work this well. And so, well, that would be one way of dealing with catching up on time. But anyway, so what is the physics? So the physics is, if this is our driving laser field, we know that when it initially enters a gas, we know that the phase velocity of light slows down in a neutral gas, just like it slows down in glass or any medium. And so the phase velocity of the laser will change depending on whether the medium is neutral or whether it's ionized. The phase velocity of light in a plasma, it turns out, is greater than the speed of light in vacuum. But in a neutral gas, it's less than the speed of light in vacuum. But the phase velocity of X-rays, remember, the refractive index is 1. So the phase velocity of the generated X-rays is always the speed of light in vacuum. And so as the medium is ionizing, and that's what's shown here in green, as the laser light is intense enough to cause tunneling, and some electron wave packet is ionized. If it returns to the ion and recombines, then the ionization drops. So you've got this stepwise ionization. In some cases, it's actually modulated. But this is a time-dependent refractive index, and most of us who would have been familiar with second harmonic generation and birefringent crystals or periodically poled materials, you would have said there is no hope of phase matching because you don't even have a constant index. But it turns out that phase matching is possible, but now in time. So on the leading edge of the laser pulse, the phase velocity of the laser is less than the speed of light in vacuum. But on the trailing edge, it's faster than the speed of light in vacuum. And so there's a certain number of laser cycles during which the laser light is traveling at the speed of light in vacuum. And that's where you do phase matching of any generated X-rays. And what's very neat about it is that that window depends on the color of the driving laser. So that immediately gives you a beautiful gate that's done optically, that we don't have to make a modulator for in the X-ray region. And so, you can take all of that physics and actually, this is a simple static balance of all the dispersion, but we worked with our collaborators in Salamanca and Luis Plaza's group to develop, quantitative propagation models. So we know we can predict that if I use this color driving laser wavelength, then I can make this color X-rays from the vacuum ultraviolet to the extreme ultraviolet and soft X-ray region of the spectrum. And the solid lines here are the theory, and the filled in lines are where we validated these theories experimentally. So in the simplest form, because harmonic generation is now very sophisticated and we can play many tricks in manipulating the light, but in its simplest form, if we use visible and near infrared lasers, then we can phase match into the extreme ultraviolet region of the spectrum. And then moving to mid-infrared lasers in collaboration with Andrus Baltuska's group, then we can get to the KeV photon energy region. Apologize about. And so we can make either these coherent supercontinua that allow us to span many elemental absorption edges. And this corresponds to a phase-matched 5,000 order process. And it turns out this is the only way to make a coherent KeV X-ray beam on a tabletop. And then I mentioned that the phase matching window depends on the color of the driving laser wavelength, and that's for photonics people, that's easy to explain. You know that the phase mismatch is proportional to the harmonic order, and it turns out that as you go to longer driving laser wavelengths, quantum diffusion also increases, so you need to increase the gas pressure. So you get two factors that multiply the phase mismatch as you go. If you want to get to a particular photon energy, then if you use mid-infrared lasers, you'll have to add many more of those together. And so you can then plot the phase mismatch for tight sapphire lasers or mid-infrared lasers, and just this multiplication factor gives you this very cycle by cycle increase in the phase mismatch, so the window shrinks. And so in its simplest form of harmonic generation, you tend to get attosecond pulse trains with tight sapphire driving lasers down to a single isolated attosecond phase matched burst if you use mid-infrared lasers. And so the character of the emission changes from peaks in the extreme ultraviolet region of the spectrum to this coherent continuum in the soft X-ray region. And then if you phase match, of course, then you will tend to generate a beam. And so using tight sapphire lasers, we can easily reach the extreme ultraviolet region of the spectrum. And then as we move to infrared lasers, we can get to 1 nanometer. Now, those of us who've been working with harmonics for a while, we think of these light sources often as very beautiful quantum physics, and perhaps maybe since they don't rival the energy per pulse of X-ray free electron lasers, we think about them as maybe not as practical for applications, but actually that's not true anymore. Now that we've figured out, now that our community has figured out how to do this process close to optimal, in the vacuum ultraviolet we're at synchrotron level efficiencies. And in the EUV, we can easily get to, even with a 1 watt laser, you're already making microwatts of power. A microwatt is what synchrotron use in their microscopes to do X-ray imaging. So the conversion efficiency is very practical. And although in the mid-infrared, for mid-infrared lasers, just because of the laser systems need to be slightly different parameters than what they are now, we expect that the conversion efficiencies of 10 to the minus 6 to 7 would be possible also, in which case we really will have tabletop synchrotrons all spanning the whole soft X-ray region of the spectrum. And so this is just showing the power levels that are now possible. So very reasonable power levels. And we've many surprises, whoops, even more. Many surprises, including the fact that if you use a very intense ultraviolet laser, we can make harmonics in the soft X-ray region, but with very narrow line widths. This is very useful for imaging or the photoelectron spectroscopies that Albert and David use. And then another advance is being able to control the polarization. This was an interesting story. Back in '95, Wilhelm Becker's group had essentially solved the challenge of how you could make circularly polarized harmonics from a single atom. So I talked about this movie before, which is what happens to the electron wave packet if you drive an atom with a linearly polarized femtosecond laser pulse. For a long time, people thought you could not make circularly polarized harmonics because if you use circular polarization, you ionize the atom, but the electron never returns. And if it doesn't return, there's no way to make your X-ray. What Wilhelm and his group had proposed is instead take counter-rotating circularly polarized beams, for example, fundamental and second harmonic. And if you do that, sure enough, you ionize the atom, but the electron also returns. So now you have a way of making a circularly polarized harmonic, and I think it's more intuitive, I think, in the photon picture. So left and right counter-rotating beams, that combined field is trifold symmetric, and you know you're going to ionize the electron at the peak of the field, and then it's going to return. So you expect to get 3 recollisions per fundamental laser cycle, but you'll also make a beautifully tailored light field because you have to conserve energy and photon spin angular momentum. And you only can, the high harmonic photon can only have 1 unit of photon spin angular momentum. It has to be either left or right circularly polarized, depending on whether it grabs 1 more blue or red photon. And so you get this beautiful spectrum where now instead of odd order harmonics, you now get these beautiful spectral pairs where each pair consists of a left and right circularly polarized harmonic. And you can play with the spacing and the separation by just changing the color of the driving laser fields. And actually, we can go a fair bit beyond this now by just also changing the angle. So really have control over the polarization and even the direction of these high harmonic beams by playing with the selection rules that light offers under these circumstances. And I mentioned that you get 3 bursts per fundamental laser cycle. And so this is actually what the waveform looks like in theory and experimentally. So you have these 3 bursts that are each linearly polarized, but phased exactly right so that the net emission is circularly polarized. And it is, this light field is changing in amplitude and color and direction on a sub-femtosecond time scale. So we think it's one of the most complex coherent fields that were produced and measured to date. And then we were able to measure this field by using essentially interfering it with a light field on a surface, because photo emission is polarization sensitive. So we could characterize the orthogonal components of this high harmonic field, and that's how we were able to make this measurement. Okay, so in the last part of my talk, I'd like to talk about just one, maybe two applications if I have time. But you know, we've been pursuing these applications for the last 15 years or so. And now I think we're, together with the other beautiful work we heard from David and here in Ottawa and elsewhere, that we really do think this light source technology has moved beyond demos, and that we really are able to uncover new understanding about materials. We're not that smart to know in advance, but it turns out if you, as the photonics community knows, if you have a new measurement capability, we can actually point it at any material and we learn something new about the material. In magnetic systems, what we can do is point it at an alloy or a multilayer, and then we can read out the magnetic state of every element in that alloy or every layer in a multilayer, and do that with femtosecond precision. And that is really nice, because if you try to read out the magnetic state using visible lasers, you average over the magnetic state, because you don't get a layer, or you can't even penetrate opaque layers, but you tend to just read out the average magnetic state. And in magnetism in particular, because it's related to the spins, the dynamics are very fast. And so harmonics are a great probe of magnetic systems. Also in thermal transport, it turns out the character of how heat flows changes in nanosystems, and we can directly read that out. There's a direct analogy here with measurement using visible lasers. And we all know that lasers are great, because if you have phase sensitivity, you can really detect very small motions. In a nanosystem, we can detect picometer displacement, so we can easily see nanostructures heat and cool, and then uncover that there's something changing in the cooling rate because of the nanostructure, for example. And you get very surprising findings, like if you pack hot structures close together, they cool faster than if you separate them. And that was definitely counterintuitive. Another example, in doped material, we found that the mechanical, particularly in very thin materials that are hard to measure using standard nano indentation, we found that the mechanical properties completely change if you dope it. The material will go from being compressible to being completely incompressible. And there's no other way to see that in very thin films. And a lot of work on photo emission in understanding how materials, what are the interactions in a material that lead to their properties. And what I'd like to talk today in the last part of my talk is on sub-wavelength X-ray imaging using harmonics, and this is the first demonstration of sub-wavelength imaging in the X-ray region. And then on my title slide, I had the joint affiliation between JILA and KM Labs for imaging in particular, particularly coherent imaging. When you're not using lenses, you have to, the beam you shine on the object has to be stable in amplitude and shape and pointing. And so bringing engineering to the systems, to these high harmonic systems, was critical. We used to build them ourselves at JILA, and every high harmonic source was a work of art, and it worked differently. And you know, we're good physicists, but we're not good engineers. We didn't know how true that statement was, But then by actually bringing in engineering designs, this is at a wavelength of 13 nanometers, we have intensity stability of less than 4%, and pointing stability also. That's as good as a laser at micron. And it turns out that in particular, spectroscopy is not quite as demanding, but for coherent imaging, if your beam changes, your image reconstruction is completely incorrect. And so this was critical for some of the work I'm going to talk about. And I like to say that we now have a complementary source to the beautiful facility scale sources that are from synchrotrons and XFELs. There, I mean, you have the really gorgeous setups. As a user, you can go in, get help from a beam scientist. But the thing I love about harmonic generation is we have that capability in the EUV and soon into the soft X-ray region. But what we also have is these light sources are great because a student can have an idea. They don't have to write a proposal, and it speeds up discovery, because if you have to convince a committee of your good idea, we've all experienced, if it's a really new idea, forget about it. Nobody will approve, give you beam time. And high harmonic generation does not have that barrier. So you can really have discovery science led by students and postdocs, which are the full, you know, that we all remember, the young people in the audience, maybe not yet, but we all remember the first time we had our idea during our PhD thesis that your PhD advisor did not come up with, and that's when you really believe you're going, you know, you're going to be a scientist. You can be a scientist, I should say. Okay, so X-ray imaging. Why is it interesting? Okay, so we know X-rays are great. They can penetrate more than electron microscopy. They can penetrate opaque materials. You have these absorption edges, for example. These are in magnetic materials in the extreme ultraviolet and soft X-ray region. So you know what is the element you're looking at, what its chemical state is, and what its magnetic state is. If you have a good microscope, you should be able to image very small features corresponding to the wavelength. And because we have high frequencies and because of the physics of harmonic generation, we know that we have light pulses now that are faster than any charge motion in any material. Okay, so why wasn't this used before? It's because in the X-ray region, if you build a microscope based on traditional optics, there are no refractive optics. Reflective optics are extremely challenging to polish. So people used diffractive optics based on zone plates. But there, your resolution is completely limited to how well you can make that outer ring of the zone plate. And for the most part, it was about 10 times diffraction limited. So the best X-ray microscope in the world, based on zone plates, had a resolution of 13 nanometers, but used 2 nanometer illumination, so 10 times diffraction limited. Fortunately, just about the same time that harmonics were being developed, this new technique that's really revolutionizing X-ray imaging and also electron imaging actually, called coherent diffraction imaging. It was proposed a long time ago in '52 by David Sayre. And the idea is you shine a beam of light onto an isolated sample and collect the scatter pattern. And if you can guess the phase, of course, you can retrieve the image. So how do you guess the phase? The initial implementation of this work used the isolation constraint. So for example, you could think about this as put a cell into a synchrotron beam, collect the scatter pattern, just assign random phases, and then recover the image. But if you knew your object was isolated, and if you have image out here, you know that's because you guessed the phase incorrectly. So you could set the outer regions here to 0, take another Fourier transform. Now you have a better guess of the phase, but you have the wrong amplitude, but you can substitute these amplitudes with the experimental amplitudes and then recover the image. So you've gotten rid of all the X-ray optics. So now the big thing is now you should be able to get to less sub-wavelength. And the other very good thing about it is that it is the most photon efficient form of imaging. There's no optics between your scatterer and the detector. That's a big deal in the X-ray region because there is, particularly in biological systems where there's an X-ray dose issue. So it's very good to be able to reduce. And robust to vibrations because you can build a microscope with 10 nanometer spatial resolution and it can be sitting on a table with no special vibration isolation. Because all that has to happen is that the beam doesn't move on your pixels, and the pixels are on order of 13 micron. So it totally changes, like, you know, for a good zone plate microscope, when they build that at Berkeley, they have to have a $10 million room. We can build this microscope on a table without any, with the roughing pumps connected directly to the microscope. So there are lots of neat things about this. And then the last thing I forgot to say was that John Miao, as part of his thesis work with Janos Kurtz, demonstrated this first using the Brookhaven, you know, an apertured version at the Brookhaven synchrotron source, and David Sayre was on the paper. So, yeah, for the students in the audience, sometimes it takes a while. Yeah, and that was his paper. That was Sayre's paper. That was his full paper. And then this is just, you know, so we can cry after, you know, getting beaten up by reviewers and such. The extension to 3 dimensions is obvious. It's just been, you know, some would claim it hasn't been done yet. Yeah. Anyway, I love this because it just makes me, you know, at least want to, yeah. Okay. Okay, so is the phase problem really a problem? I know many people do phase retrieval with Frog and other, but this is just, you know, boy, okay, well, let's just go with it. We have our object, make a Fourier transform, keep the amplitude, but get rid of the phase, and we get a blob. If you do the same, but now keep the phase and just put a uniform amplitude everywhere, and then take your Fourier transform, you can sort of recognize that there are 2 bunnies here. You've lost the orientation, but you can see that the phase is everything. In the initial implementation of this coherent diffraction imaging, the algorithms were not so robust. So what people would do is they would take a scatter pattern and they would run 200 different phase retrieval cycles to their convergence, and then they would average. The problem with that is that no material scientist wanted an average image of their sample. So it was poo-pooed for a long time. And then Rodenberg's group in the UK and some others came up with this technique called tychography, where now the constraint is not isolation, but rather scan your beam with 80% overlap, and now you've over-constrained the problem. So it sort of forces the algorithm now to converge, and that's opened up a lot of advances. For example, you can now put a material, since you don't need to an isolated sample, you can put a material system into your microscope. And so this is the tychography, just a little movie. So it's more intensive in terms of scanning and data acquisition. And then to do the phase retrieval quickly, you have to use parallel GPUs. But that of course, is becoming more and more possible now. And so that's what we use now with our high harmonic beams. We take a few multilayer mirrors at 30 or 30 nanometers. You can get some reasonable reflectivity there, and we can make these microscopes either in reflection or transmission, and these working distance are an order of 10 to 20 centimeters. So very large depth of field. So it just makes the imaging nice. If you want super high spatial resolution, then you need a very high NA. Then you need to put your detector very close to your object, which is what we did here in a microscope, where we really pushed the NA to 0.54, and then and so in terms of the spatial resolution that's possible using these coherent diffraction imaging techniques, we started out with thesis work from Richard Sandberg that we had a spatial resolution of 200 nanometers, you know, not anything to write home about, but now we have 12.6 nanometer spatial resolution at 13.5 nanometers, and that's a factor of 6 better than the best microscope that anybody has demonstrated at these wavelengths, or the best one you can buy from Zeiss. So it's 50 to 80 nanometer using traditional zone plate microscopes, but 0.9 lambda. And there's no reason that can't push down to close to lambda over 2, or that super resolution, could be implemented in the X-ray region. But as well as just the spatial resolution, I think what we've slowly learned over the past. So this was the first image that John Liao made, and what we've learned to do since 2007, so 10 years, is just to really improve the actual image quality. So we can and validate that using other imaging techniques. What people don't tell you is that and some of you who do materials might know this, but AFMs damage a sample and SEMs contaminate it a lot, and also are very sensitive to the view. But they're the best we have, and so we compare our images with those other images. So here's a comparison. This was the first image where we thought, light is better than electrons for these tabletop sources. So this is the coherent diffractive high harmonic phase image, and this is a scanning electron microscope image. Of the same sample, it's just little nanostructures our students, as Chandlat, made on a silicon wafer. And in an electron microscope, the contrast mechanism is that the electrons will bounce off different areas of the sample with different amplitudes. But on the CDI image, the phase contrast is due to the short wavelength of the light. And so you can see here, you can just see these, the contrast is just much, much better on the light-based microscope. And it has a larger working distance. And in our work to date, which this is relatively new work from 2015, but we do think it does less damage than AFM or SEM. And then you can take these phase images, and you also get an amplitude image because you get the amplitude and phase. And so we can translate those into height maps or chemical maps, and then we can image through buried layers. Also because, of course, EUV penetrates, and so we can image, so this is an image of a nanostructure that's been overcoated with aluminum. And so what you're seeing is the buried interface through an opaque material. And in fact, this is the uncoated and coated, and the contrast shouldn't change. This is the amplitude image, but it changed because there was diffusion at the buried interface. So it's a very nice, unique capability. And then our highest spatial resolution image is shown here. So this was done using 13 nanometer beams, because you can get really good mirrors there. That's why they picked that wavelength for EUV lithography. You can get the 70% reflective mirrors, which of course are not good, not good for in terms of a visible mirror, but in the EUV, that 70% is really good. And so we used a zone plate as a sample. It's a nice high contrast sample, and this is the SEM image in reflection, and this is the CDI image in transmission, so the contrast is flipped. And so you're looking, but we can make a nice height map. We have to do fancy things with the algorithm, because if the sample is nearly periodic, there's very little diversity in the scatter patterns, and so you have to help it. So we help it by feeding it the beam, which we can take a picture of the beam with the CCD camera, and we can show that, sure enough, every way we look at these images, we can quantify the resolution very carefully. And we've taken our first movies. So this is a nanostructure being heated by a femtosecond laser, and this is a little stroboscopic movie that shows the thermal expansion and then acoustic wave propagation in the nanostructure. It might look a little bit primitive. It turns out that you can't calculate this. It's a V-shaped nanostructure, and the acoustics are so complex that the best codes can't actually predict it. So it was one case, it was very painful to make the movie, but it turns out it's the only way to see how the nanostructure behaves. So that was, interesting. And of course, as we all know in this audience, everything scales with the wavelength. And so that work was done with 13 nanometer beams. And so now we can make 1 nanometer wavelength beams. So we should be able to make microscopes, particularly as you go to below 4 nanometers, materials become very transparent in the soft X-ray region. So, so the next step will be, functional imaging of 3D materials. So I've told you how we can push the spatial resolution in imaging using these short wavelength beams. It turns out that we can also push the temporal resolution of measurements also by taking advantage of their very high time resolution. I won't go into the details, obviously, but I just wanted you to look at the y-axis on this graph. So it goes from 1 attosecond to a femtosecond to a picosecond. So what it's showing is electron-electron interactions in a material, and how we've used angle-resolved photo emission to actually be able to quantify electron-electron scattering and screening in these quantum materials. So this is the only way we know that can distinguish charge scattering that is well known in any of your condensed matter textbook, well known to be sub-attosecond. But screening has a response time of half the plasma period of about 300 attoseconds. But this is a way to directly measure the electron-electron, what's called the Baer-Coulomb electron-electron interaction. And once you know that, then you can go near the Fermi level to really see in what materials are charge screening important to their functional properties. And then we want to do, of course, apologize again. Of course, now we have the ability to make high spatial resolution measurements and high temporal resolution measurements. What we want to do now is sort of combine them to make functional imaging microscopes. But we know that using X-rays, we might be able to get to spatial resolutions of a few nanometers. And if we want to do better, we probably have to use the same laser to also make ultrafast electron bursts. So then by combining X-ray, nano-optical, and electron microscopy, we should be able to image functional non-crystalline materials in real time. This is a 10-year grand challenge, and NSF is going to, we were very fortunate that after our third try, we got an NSF center to try to do this, and we're working very hard to try to keep NSF happy. And then just finally, so what technology will enhance our ability to make measurements, or maybe make this quantum technology accessible, is these fiber laser technologies. They've been around for a long time. People have talked about them for a long time, but they finally, the technology for the 100 femtosecond class systems that you need to drive these high harmonics, they're finally there. And so now you can sort of have a little fiber laser box that's very small that covers from the mid-IR to, let's say, the vacuum ultraviolet region of the spectrum, and a slightly bigger box, but not terrible, to get to the soft X-ray region. And so these are going to be available within, some are already available, and some will be available within a year or so. And so that will help other areas of science be able to benefit from these essentially tabletop synchrotron sources. So I hope I've at least given you, some insight as to why we think high harmonics, they're a beautiful quantum light science technology, giving us, very surprising and ultra precise control over light in the soft X-ray region. The limits of this high harmonic quantum technology are not known, because to do that, to really predict, you would need to combine 3D Schrodinger, time-dependent Schrodinger equation with Maxwell. And there is no computer that can do that now. And so that's, for that reason, there's only approximate estimates of where the limits might be. but even the back of the envelope tell us that that might be 15 kV, and that even if it were that, I'd be very happy. If it were 50 kV, it would even be better. It's already giving us useful insights into the molecular, condensed matter, and material science, and having an impact also on imaging. And with that, I really need to finish by thanking many students and collaborators who many of these students are now on to bigger and better career steps. But in particular, Zhao Xi, who developed the harmonic source at KM Labs, and Sterling, who's just amazing in terms of his laser technology, Charles Durfee at School of Mines, Oren Cohen, and Ofer Kiefer, who we worked with on making circularly polarized harmonics, Carlos and Luis, who worked on modeling phase matching, and then Andrus Baltuska, who we demonstrated the KEV harmonics with, and then our other colleagues who've helped us on materials and molecular systems. And I'd like to thank you very much for your attention.
If you want to compare it with STED microscopy, because I mean, the energy that you have, it is much higher than, for example, STED. And in STED, you can get exactly the same resolution. So I'm sure that there is benefit with your technique.
Spatial resolution, yes, exactly. So of course, of course, the time resolution is an obvious one because we have femtosecond time resolution. But I think, and of course, with some of the, you can get chemical elemental resolution in some other microscopies also. But I think the ability to so certainly for metrology at 13 nanometers, this is a nice option. And also, of course, in the soft X-ray region, you can just look at a thicker sample. So there's no perfect imaging technique. In fact, for many materials, you want to look at them several ways. And in fact, we were talking a little bit about this earlier. I mean, the big issue with some of these quantum materials is that nobody has any characterization on their growth chamber. So it's just like, and this is well known in quantum materials area, that so every new sample is a work of art. And then the poor probers then go and probe it, and then you don't know if your probe technique is not working or if the sample is different. And so that's well recognized, and the need to couple a characterization with synthesis and then theory is well recognized in materials. So there, it's going to be an all of the above approach to try and, make progress in some of these advanced material science.
So you say that the phase matching window depends on the wavelengths for micron gives optimal phase matching, but the way you explain it seems also that it depends on the slope of the ionization front.
Yes.
And somehow also, therefore, on the pulse shape in the temporal profile.
A little bit, yeah. A little bit on the pulse. Yes, you can certainly adjust it that way. But I was just doing the simplest case where you don't cross beams or you don't do anything fancy. Let's just say it's a Gaussian pulse, just for comparison. But you can certainly influence it with the pulse shape and with multicolor. Geometry, So that's the wonderful thing about harmonic generation is that we really can control the X-rays with the visible light, and that's very good because the alternative is either impossible or very expensive.
Well, Margaret arrived last night, very late in the evening, and she leaves almost immediately after the talk. So I think we need to give a very special thanks.